For 10,000 years, while empires turned to dust and stars burned out across the galaxy, one ship remained, silent, waiting. It drifts before a white dwarf that should have been forgotten eons ago. A dead star and the last pulse of a dead empire standing guard over it. This is the destroyer Karos 9, and for millennia it has done nothing but wait. But something is now approaching the core, and deep inside its hull, systems that have not stirred in 10,000 years are beginning, faintly, to wake. Today we investigate the one system that makes that reawakening possible at all, the reactor that never fully died, and the fragile process of bringing a 10,000-year-old power core back to life without tearing the ship apart from the inside. Inside the ship, one system never fully went dark. A low-power watchdog loop, trickle-feeding just enough current to a handful of sensors and a single dormant capacitor bank. For 10,000 years, this loop has done one job only: wait for a trigger and hold the line just barely alive. That trigger has now arrived. Deep in the ship's midships chamber, the reactor core begins its first pre-ignition diagnostic in 10 millennia. This is the moment every later system depends on. Weapons, engines, life support, none of it matters if this core cannot restart without fracturing under its own stored heat. Bringing a fusion reactor back from a decade-long shutdown is already a delicate operation. Bringing one back after 10,000 years is something no engineer has ever actually attempted. Commander Elara Voss is the only living presence aboard, not the ship's original crew, but a caretaker awakened generations after the ship first went dark, bound to the same long watch. She stands on the command deck as the first diagnostic alert in 10,000 years crosses her console. To understand what she's about to attempt, we need to understand what a reactor actually is. A controlled fusion or fission process that converts nuclear energy into heat, and that heat into electrical power. Karos 9's core has spent 10 millennia in the most extreme version of standby mode ever engineered. Not truly off, but suspended just above the threshold of death, its fuel intact, its containment sealed, waiting for a command that was never expected to come this late. Standby mode sounds simple, but for a fusion reactor, it is one of the hardest engineering problems in the entire ship. A reactor that runs hot stays stable. Its materials expand evenly, its coolant flows continuously, its systems self-correct. A reactor held at near zero for 10,000 years faces the opposite problem. Metal fatigue from millennia of faint vibration, superconducting cable that can quietly degrade without constant current, and capacitor ceramics that grow brittle in cold and dark. Voss's console shows dozens of systems reporting their status for the first time in recorded memory, and roughly a third of them return no answer at all. The question this episode must answer is not whether the reactor can restart, but whether it can do so without a repeat of the very disaster that left this ship the last of its kind. Before Voss can risk a restart, she has to understand exactly what she's restarting. Karos 9's reactor isn't a modern design. It's a relic, built by an empire whose engineering conventions are now archaeology. Its core uses a magnetically confined fusion chamber, ringed by superconducting coils that once needed constant cryogenic cooling to function. 10,000 years without that cooling should have destroyed the coils outright. Instead, the ship's builders anticipated exactly this scenario: a secondary passive shielding layer, thick radiation-hardened alloy wrapped directly around the coil housing, designed to let the coils survive centuries of neglect by trading efficiency for endurance. It's a design philosophy modern engineers still study. Build not for peak performance, but for the possibility that no one will ever come back to maintain you. That philosophy explains why the coils are intact, but it doesn't explain everything Voss is seeing. The capacitor bank beside the reactor, the array that will eventually store and release power to the weapon spine, uses a ceramic dielectric material that shouldn't have survived this long without microfracturing. Real ceramic capacitors, even well-engineered ones, degrade under thermal cycling over years, not millennia. So either Karos 9's builders solved a materials problem no modern engineer has fully replicated, or Voss is about to charge a component that will fail the moment real current runs through it. This is where the episode draws its clearest line. The reactor shielding is grounded in genuine aerospace engineering. The idea of a ceramic capacitor stable for 10,000 years is not. It's the one deliberate leap this story asks you to accept.
Voss makes her decision. The restart sequence begins the way every fusion ignition begins, ancient or modern. The capacitor bank discharges a massive pulse of stored energy into the reactor's initiation coils, compressing and heating the fuel past the threshold where fusion becomes self-sustaining. On a modern ship, this is a routine computer-verified procedure. On Kairos 9, it's a gamble on materials no one has stress-tested in 10,000 years. The first pulse fires. Lights along the capacitor housing flare a cold blue-white, and for a fraction of a second, the entire chamber holds its breath, the ceramic dielectric under more electrical stress than it has experienced since the ship was built, the ancient superconducting coils carrying current for the first time in recorded memory. On the command deck, Voss watches temperature and pressure readings climb through ranges the ship hasn't reported in 10 millennia. This is the moment every failure mode we've discussed could turn real. A fractured capacitor could discharge unevenly and rupture. A weakened superconducting coil could quench, dumping its stored magnetic energy as a destructive pulse of heat. But second by second, the numbers stabilize instead of spiking. The fusion chamber holds. The ancient shielding does exactly what its builders designed it to do. It's not victory yet. The reactor is alive, not fully operational. But for the first time in 10,000 years, Kairos 9 has a heartbeat again. And a heartbeat is the one thing every other system on this ship, weapons included, has been waiting for. A stabilized reactor is only half the problem. Raw fusion power is useless until it can travel from the core to everything that needs it. And that journey runs through the ship's power distribution bus, a network of superconducting cable that hasn't carried a meaningful current in 10,000 years. Voss watches as the ship's watchdog system begins routing the first trickle of real power outward from the reactor chamber, deck by deck, testing each junction before committing more current. This is deliberate caution, not weakness. A sudden full power surge through degraded cable could vaporize a junction and cut the ship's power in half before it ever reaches the weapon spine. So the ship does what any well-engineered system should. It verifies before it commits. One by one, junctions report back stable. But midway along the bus, a single connector fails the test outright. A superconducting joint that degraded past the point of safe use. Its material embrittled by 10 millennia of faint temperature drift with no active cooling to protect it. This is exactly the kind of localized failure real long-duration spacecraft systems are engineered to expect. The watchdog system doesn't force power through the damaged junction. It reroutes around it, sending current along a secondary path built into the original design specifically for this scenario. It costs the ship a fraction of its total power capacity, but it keeps the network alive. Redundancy, not brute strength, is what has kept Kairos 9 functional across 10,000 years of silence. With power now reaching the ship's forward sections, one system finally receives current for the first time in 10,000 years. The dorsal weapon spine. This is the moment the opening hook promised, ancient weapons waking up. But the engineering reality is quieter and more precise than spectacle. The weapon spine's own capacitor conduits begin a slow, segmented charge, drawing power in careful stages rather than one continuous surge, mirroring the same cautious approach used to restart the reactor itself. Voss watches the spine's status lights shift from dead black to a faint, cold blue-white glow, one segment at a time, moving from the ship's midsection outward toward the bow. It's not activation. It's the first stage of a much longer process. Verification before commitment, exactly as the reactor required. From the command deck, Voss watches the glow crawl forward along the spine, each segment a small confirmation that the ship's oldest, most dangerous systems are still structurally sound. She allows herself something close to relief, not because the ship is ready for what's coming, but because for the first time in this entire restart, a major system has activated without a single failure. The reactor holds.
The power bus holds, even with its one rerouted junction. And now the weapon spine, the very thing this whole investigation was chasing, is proving that 10,000 years of dormancy didn't erase what this ship was built to do. What remains is the hardest question of all: whether a system built for a war that ended millennia ago can still function under real operational stress. No restart of this scale happens without cost, and this is where Kairos 9 faces its most severe test yet. As the weapon spine's charge reaches its final segments near the bow, sensors detect a sharp temperature spike in the rerouted power junction from Deck 3, the same connector that failed verification earlier. The secondary pathway was never designed to carry this much sustained current for this long. Under real load, it's running hotter than any safety margin the original engineers accounted for. Voss watches the number climb, and for the first time since the reactor ignited, the ship's automated systems flag a genuine emergency. Continue the weapon spine's charge and risk burning out the ship's only functional backup power route, or halt now and leave the spine at partial power, exactly when it may be needed most. Voss makes the engineering call, not the dramatic one. She orders the weapon spine's charge sequence paused at 90%, redirecting excess current away from the failing junction before it reaches critical failure. It's a controlled compromise, the same principle behind every circuit breaker and thermal cutoff ever designed. Better a system that stops itself than one that destroys itself trying to finish. The junction's temperature begins to fall. The spine holds at 90% charge, dormant but ready. Its final segment near the bow left dark. It isn't the full reawakening the ship's builders intended, but it's enough. Real engineering, ancient or modern, has never been about pushing a system to its absolute limit. It's about knowing exactly where that limit is and respecting it. Bring it all together, and Kairos 9's reawakening tells a very specific engineering story. A watchdog loop that never fully died. A reactor shielded not for peak performance, but for pure, patient survival. A power network built with redundancy deliberate enough to root around its own decay. And a weapon system honest about its own limits, willing to stop short of full power rather than destroy itself, proving a point. None of this was luck. Every piece that let this ship wake up after 10,000 years was a decision made by engineers who understood they would never be there to see it happen, who built not for their own war, but for the possibility that someone, someday, might need this ship to still work. Today, that someone is Commander Ilara Voss. We haven't explained everything this ship can do. Its weapons targeting, its hull armor, its propulsion, all remain sealed behind systems this episode never opened. What we've traced is the one chain of engineering that made everything else possible. Power, restored carefully enough to survive its own restart. Whether Kairos 9 is ready for what's approaching the core is a question for another investigation. For now, what 10,000 years couldn't kill wasn't the weapons, and it wasn't the armor. It was a reactor built to wait, a network built to bend without breaking, and the quiet, patient engineering of people who never expected anyone to need what they built. Until, 10,000 years later, someone finally did.